So now we can go into the discussion of how do we actually use the validation not just on model selection but also on regularization. In particular, in regularization, we have this regularization parameter, lambda. How do we choose the lambda for the regularization? And there we want to introduce a concept called the cross-validation. Okay, so what is cross-validation? Cross-validation is one variation of the validation techniques that we have described. So instead of just fixing one part of the data set for validation, you are going to shuffle all these validation and training sets. So the problem can be considered as the leave one out approach. Suppose you have the data set that contains n samples. We will knock out one samples, as I'm showing you here, that I'm knocking out xn and yn. So let's remove that. And then you remove that sample. And then you're going to learn the hypothesis using the data set that does not contain the xn. And then what? And then you're going to compute the error. The error will be the validation error with respect to this g minus n, where this g minus n denotes that it is a hypothesis learned using a data set without the nth sample. So at this point, you ask, how many errors are there? Well, there will be n error associated with this data set because you have capital N number of data points, and since you're knocking one out, then you have a set of small ens where n will go from 1 to capital N. So which one that you want to pick? Well, you want to calculate all these ENs, and then you want to calculate the average of all these ENs. And once you calculate the average of all these ENs, that will return you a score. So cross-validation says that you have a sequence of error, E1 through En, and then we want to compute a thing called the cross-validation error. And the cross-validation error is defined as the average of all these individual errors. And so you take the sum and divide by n, where n is the number of samples in your data set. Now I'm dividing by 1 over n because I'm doing a leave one out approach. So at the end I have n of these errors. So now here, this is an example showing you what will happen if you only have 2 data points in your data set, and then you have 3 data points in your data set, and then you use 2 to do the training, and then 1 to do the validation. You can get one number. Now clearly this is not a very good choice, because if you only use one number to do the validation, how reliable can that number be? Cross-validation says that I'm going to shuffle the rows of training and also the validation, and I'm not going to just use this data point 1. I can also say that I can use the data point 2 for validation, or I can use data point 3 for validation, and then I can calculate the error. Once I have calculated the error, I can take the average, and then that will give me the cross-validation error. So the validation is to use the k samples to validate, and cross-validation says that I'm going to recycle the n samples to validate. So let's look at the example of cross-validation for linear regression. Let's recall that in the linear regression model, we have this problem of finding the W star equals to the A transpose A lambda I inverse A transpose Y. That is our linear regression model. So we can ask, what would be the optimum lambda that you can find out from this equation? So what you can do is that you can calculate H lambda, okay, where H lambda would be this matrix that associated with the equation here. Okay, so you have one more matrix A in front of that matrix. I call it H. Okay, so that would be a matrix. However, also parameterize it using lambda, because as my lambda changes, then my H will also change. Then I also define my prediction of Y hat, which is the H times Y. Okay, because that would be my W star times the A matrix. That will give me my prediction. So you can calculate the cross-validation score as follows. You can show that the cross-validation score will be given by the summation. This is a leave one out approach. So it will become yn hat minus yn divided by this 1 minus hnn. This hnn is the nth element of the matrix. Okay, so this is the diagonal element of that matrix. So you can show that. You can furthermore, you can show that this HNN, if you plug into the equation, this is really given by this result. Now, how do we prove this cross-validation score? You can see the textbook problem 4.26. Now, the message here is that here, this number is a function depending on lambda. So as you change the lambda, this cross-validation score will also change. And therefore, among all the possible lambdas, you will be able to pick one that can minimize the cross-validation score, and you will use that lambda and then put into your linear regression model and then use it as your regression result. Okay, so you can also generalize this idea to a v-fold validation. Instead of just doing leave one out, you can also say that I'm going to divide my entire data set into different blocks. And each block, I may have not just have one data point, I may have 5 data points, 10 data points, or as many data points as you want. Okay, so then you will allocate the data set into, in this example, you divide it into 10 chunks, and then one chunk you say that will be used for validation, and then the rest you will use it for training. So leave one out says that you have n training sections, so each section has n minus 1 data points. And then in practice, you can partition into V sections, and so then you can choose n divided by V points in each section, and then training using the rest, and then you can do different combination of all these validation and training sets. So that will also help you do the validation. The benefit of doing a V-fold validation compared to leave one out is that if your training data set is really, really large, then leave one out will take you a long time to compute the actual error. But if you use this V-fold validation, you just need to worry about a finite set of validation sets. So that would be a lot more computationally efficient. The rule of thumb of choosing this V-fold cross-validation is normally choose V to be 10. Now, again, this is a heuristic. This is a more based on our experience than any mathematical justification. Usually, V equals to 10, that's usually a good choice. So when you do the problem, what you can do is that you look at the data set, divide into 10 blocks, and then start to do the cross-validation. By calculating, by using one block as the validation set, and then the remaining as the training. You train and then you shuffle their rows, and then after these shuffles, then you can calculate the overall validation score, and use that validation score to choose the regularization parameter and do other fine-tuning of your model. The bottom line is that never try to use your testing data sets as part of your training procedure. You are allowed to use the validation, but you are not allowed to see the testing data set. So to summarize, validation says that let's break the data set into testing and validation, and then we are going to use the validation set to select models and then choose model parameters. And then the way to do that is just to calculate the validation score. In some situations, the validation score can be computed using the closed form expressions like in the linear regression model. In some situations, that you may just want to calculate the in-sample error using the validation set to calculate the numerical values with the hope that your numerical value will be close to the actual testing error. Now, to make this happen, of course, you need to reserve enough enough samples for the validation set. So that can be done when you are really doing a big problem. Your data set is big enough, and so in the validation set, that validation set contains enough samples. Now, remember, whenever you do this validation, keep trying to reuse the data set and report the final hypothesis. Now, in big data problems, you may not run into this issue. However, when you have a small data set, then recycling of the data usually is a very, very important thing to do. You can also use cross-validation to get a better estimate of the outsample error. Now, cross-validation, you should understand that it is an improved version of the basic validation error. The price you need to pay is that you need to use a lot more computation. You need to shuffle them, and then you need to repeat the calculation multiple times. And then let me just remind you once again that the bottom line is to never try to use the testing error, never use the testing data for validation. So that summarizes our discussion of the validation. So I hope that I have given you an overall view of what do we do when you have overfitting problem using regularization techniques, and then now when we have the validation techniques to select the model parameters. So that will give you a complete pipeline of dealing with situations that you have noise when you don't have enough samples and when you have a very complex target. I encourage everyone to take a look at this chapter of the textbook, chapter 4.3, to gain more details. In the appendix of this set of slides, you will also see some additional derivations of the unbiasedness of the cross-validation, which you can see all the details as follows. So I will encourage everyone to take a look at all these derivations as well.